we've seen that the first derivative tells us the nature of the gradient of a function. The second derivative tells us about the concavity. I'll explain what I mean by that. If we have a function that looks like this, so we've got y, some function of x, and it goes a little bit like that. We could actually do a plot of dy dx. So at corresponding x values, we can do a graphical representation of what's happening to the gradient. Now, as you can see, the slope here, which is dy dx, so at that corresponding point down here, the gradient is quite large. The rise over run, just imagine that's tangent here, would be quite large. So if I was plotting for the corresponding x values here, dy dx, we would have the graph starting up there quite large. And then the gradient gets less and less and less, it decreases. So to represent that, we could just do something a little bit like that. All right, so up here, the gradient is approaching, and this is dy dx, this is the gradient here, it is approaching 0. So that would be 0 gradient if it actually cut that line there. Okay, what is d2y dx2? Well, it is the derivative with respect to x of dy dx. In other words, it is the gradient of this line here, this curve. So d2y dx2 is the gradient of the dy dx curve. Now, the gradient everywhere along here, which is d2y dx2, is negative. So working backwards, if d2y dx2 is negative, in this case here, we have an original function that is what we call concave down. It is, the cave is opening down. So the original curve, or the function, is concave down. It is opening towards the bottom. The other scenario is if we've got a curve that looks a little bit like this. So here is my y versus x. Let's once again do the dy dx versus x. So dy dx is the gradient of this. Here it is quite small, so corresponding x value down here, well, the gradient is small, it is almost equal to 0. And as we get up to here, it gets quite large. So it's going to look very similar. Won't be a mirror image, but it'll look pretty close to it. Now d2y dx2 is the gradient of the dy dx function. And everywhere there, it is positive. The original curve, then, is concave up. Just working backwards there. So we've worked the nature of the second derivative, which is the gradient of the dy dx function. We've said it's always positive here. So if this d2y dx2 is positive, then the original function is concave up. That way. All right, so let's apply that though to what we can do with our curve sketching. So we can do what's called the second derivative test. If you've got dy dx d2, so if you've got a turning point, so you know somewhere on the curve dy dx equals 0, and the second derivative is negative at that particular point where dy dx is equal to 0, because it is concave down, therefore we have a local maximum. All right, now we've used the first derivative test prior to this, and we substituted x values either side of where dy dx equals 0 to work out whether we have a maximum or minimum. This is another way, probably a quicker way, of being able to determine whether we have maximums or minimums. So if dy dx is equal to 0 and d2 y dx2 is negative, the second derivative of negative means it is concave down, so we must have that sort of situation, so we have a local maximum. The other part of the second derivative text, if dy dx equals 0 and the second derivative d2y dx2 is positive by substituting the x value that makes the dy dx equals 0 into the second derivative, and we get a positive value. Therefore, we get concave upwards, and therefore we get a local minimum. So that's if d2y dx2 is negative, positive. We have a third scenario, and that is if dy dx equals 0 and d2y dx2 is not negative, not positive, that means is 0, then we have to use the first derivative test. And the first derivative test is when we substitute x values either side of the x value that makes dy dx equals 0. So we use the first derivative test. We have to go back to that, and we can't use the second derivative test. So this test is worthwhile committing to memory. As I said, there are three scenarios. If we get the second derivative equals 0, then we've got to go back and use the first derivative test to determine whether we have a local maximum, local minimum, or a third scenario, and that could be a point of inflection. All right, so concavity, concave down means the original graph will be open towards the bottom of the page. Concave up means that the graph opens towards the top of the page. If we've got the second derivative negative, then the original graph will be concave down, and if the second derivative is positive, the original curve will be concave up.